Greetings everybody, and today we're going to be evaluating these two improper integrals, the integral running from 0 to infinity of sine of x to the n as well as cosine of x to the n, where n is any real number that's greater than 1. So I guess I'll just call these generalized Fresnel integrals because the Fresnel integrals are the case where n over here and here is equal to 2, but here we're just having any power of n that's greater than 1. And I have done a video on the Fresnel integrals, and we're going to be using a similar method, namely complex analysis and contour integration. So first of all, if we want to use complex analysis, why not kind of combine these two integrals together? And notice that for the sine of x to the n, that's exactly the imaginary part of the function e to the I x to the n, and for the cosine of x to the n, that's exactly the real part of e to the I x to the n. And we can kind of combine these two together by just taking a look at the function e to the I x to the n. So we're going to be taking a look at the integral from 0 to infinity instead of e to the I x to the n. And just like I said before, now if we take the real part of this integral, we get the cosine integral, and if we take the imaginary part of this integral, we get the integral with the sine in it. So this is a nice kind of generalization. So how do we evaluate this integral? Well, it's a bit difficult to do, first of all, but my goal is to kind of transform this integral into an integral of the form 0 to infinity of e to the, I guess, minus t to the n, let's use a random variable t, dt. So if we can somehow turn this integral into an integral of this form, we can actually use a nice substitution and obtain some kinds of gamma function at the very end. So our goal is now to somehow transform this integral into e to the minus t to the n. And the first step, I guess, to do this is, well, we want a negative over here. So why not just introduce a negative in the exponent? So we have the integral from 0 to infinity of e to the minus, and then we can't just put a negative in, we have to kind of counteract that with another minus, a minus I, and then x to the n, like so. So these two integrals are still the same thing. Okay, and now I want to have something to the nth power. So I want to turn this inside into something to the nth power. And I guess the first thing to do is to get rid of this minus I, because that's kind of annoying. So we can rewrite this integral as the integral from 0 to infinity of e to the minus, and now we're going to turn minus I into polar form. So that's exactly e to the I minus I, actually, pi over 2, and then x to the n dx. Alright, and now this is a little bit better to work with because this is in power form, we can deal with powers a lot more easily. So I want you to notice that if we have e to the minus I pi over 2, if we divide this fraction over here by 2 by n, so 2n, and we multiply by n, that's the same thing, and we can kind of interpret this complex number as this e to the minus I pi over 2n, but the whole thing raised to the nth power. So this complex number over here is the same thing as this complex number here, and the reason why we want an nth power is to match with this x to the nth power, so we can kind of combine those two together using some exponential properties. So let's plug that in. This is now equal to the integral from 0 to infinity of e to the minus, and now this is going to turn into e to the minus I pi over 2n times x, and then we can raise all of this to the nth power. So we had something raised to the nth and x raised to the nth, and we can combine those two together into that whole junk but raised to the nth power. Alright, and as you can see, we're basically in this form over here because we have the integral from 0 to infinity of e to the minus something raised to the nth power, and let's just do a substitution to kind of reduce this something into one variable. So I guess we just let's call it z be equal to e to the minus I pi over 2n times x, which means dz is equal to e to the minus I pi over 2n dx. And if you kind of isolate or x, solve for our x, you get that dx is equal to e to the I pi over 2n times dz. And I want to make one small modification to this integral. Instead of having this upper bound as infinity, I'm just going to call it r, and we're going to put a limit outside. So we're going to have the limit as r approaches infinity on this integral. So that's really the same thing. Let's make the clearer r. Okay, and now let's plug everything in. So now we have this integral is equal to, we have the limit as r approaches infinity, and we'll worry about the bounds later on. Let's worry about the integrand first of all. So now we have the e to the minus, and this whole thing, we substituted that for z, so e to the minus is z to the n, and then dx becomes e to the I pi over 2n times dz. And now how about our bounds? If we plug 0 into this x, our z is 0, because 0 times anything is 0. But if we plug r into here, then we get some weird complex number. It's actually going to become r times e to the minus I pi over 2n. So kind of pointing in some weird direction in the complex plane. So this is what we have right now. We're just going to keep this limit. So now we can write this as the limit. Actually, let's bring this constant out to the front. So we have e to the I pi over 2n, and then a limit as r approaches infinity on the integral from 0 to r, e to the minus I pi over 2n times e to the minus z to the n dz. Right, that's quite nice. We have the integrands that we want. This is, remember, this is the integral that we want to end up with e to the minus something to the n. That's exactly what we have. But the problem is the interval of integration. It's pointing in some weird direction in the complex plane. And what I want to show now is that it doesn't actually matter what direction you point in the complex plane. You can actually get it to point in just the real axis. So let's get rid of all of this. So if we take a look at our complex plane, this is our complex plane with the real axis and the imaginary axis. What exactly is this path in the complex plane? Well, we're going to from 0, and we're going down. This is e to the minus I pi over 2n. So it's some complex number with a negative argument. So maybe down here somewhere. So this is our path of integration. And of course, this distance right here is r. So this complex number is r times e to the minus I pi over 2n. And we don't really want to integrate on this path. Instead, we want to integrate on this path from 0 to r on the real axis. Because remember, our goal integral is the integral from 0 to infinity of e to the minus t to the n dt. And if we integrate from 0 to r on the real axis and just simply apply this limit, then we get our integral that we want. Okay, and I want you to notice one more thing as well. The function we're using, e to the minus z to the n, that's an entire function because, well, this polynomial function is entire and then the exponential function is entire. So if you compose those two together, it's still an entire function. So everywhere on this complex plane is analytic. So we can actually make use of Cauchy's integral theorem. And the Cauchy's integral theorem says that if you have the contour integral along some closed loop C of our function f of z, and in this case, our f of z could be e to the minus z to the n. If f of z is analytic everywhere, then this integral just becomes 0. And this is very useful because now what we can do is if we construct a closed contour, let's call this whole entire contour over here C, and let's call this path that's going down here psi. So I guess we can rewrite this integral, we can rewrite it as the integral over psi of e to the minus z to the n dz. It's the same thing, we call this path psi, and we can call this path out here gamma. And then obviously we have this interval on the real axis. So notice if we decompose this contour integral, we have the integral over psi of f of z dz plus the integral over gamma of f of z dz plus the integral, and now we're going from r back to 0, so from r to 0 of f of z dz, that's all going to be equal to 0. And at first this might not seem that interesting, but notice, let's chuck this integral, this is kind of like our goal integral, onto the other side, and we get that the integral over psi of f of z dz plus the integral over gamma of f of z dz is equal to, now we have minus this integral on the other side, but we can use that minus to flip the bounds, so we have the integral from 0 to r of f of z dz. And notice on the integral over psi, this is integral on the path psi, we also applied the limit. So if we apply the limit everywhere, we have the limit as r approaches infinity on this whole left hand side, and we have the limit on the right hand side. That's the integral from 0 to infinity of f of z dz. But since we're on the real axis, we can kind of replace everything with x's or something like that. So this integral on the right hand side is basically our goal integral. So the integral from 0 to infinity of e to the minus t to the n dt. We can call it that. Okay, and as you can see, we have this nice relationship between the integral over psi and our goal integral. We're just off by this integral over gamma. And in fact, if you apply this limit as r approaches infinity on the integral over gamma, it actually vanishes off to 0, and hence you can show that the integral, our integral that we have right now, in the limit as our r approaches infinity, is really the same thing as the integral from 0 to infinity of e to the minus t to the n dt. So these two integrals are the same thing. So what I want to do now is I want to show that this integral over gamma does indeed go to 0 in the limit as our r approaches infinity. So let's write down our result that we have so far. So far we said that the integral from 0 to infinity of e to the I times x to the n dx is equal to e to the I pi over 2n times the limit as r approaches infinity on the integral from 0 to r e to the minus I pi over 2n times e to the minus z to the n dz. So this is what we have so far. We have this relationship. And now our goal is to show that the integral over gamma goes to 0. So we want to show that the integral over gamma of f of z, but f of z in this case is e to the minus z to the n dz. I want to show that in the limit, this integral is equal to 0. So what exactly is our path to gamma? Because if we know what that path is, we can parameterize it. Well, if we look on our complex plane again, this is our path psi, and this is our path gamma, like so. And notice that psi goes up to the point r e to the minus I pi over 2n, which means that this angle over here is exactly pi over 2n. So if we're traversing the path in this direction, this is our contour path, then our gamma starts from an angle of pi over 2n and it goes up to 0, and of course it has a constant radius of r everywhere. So whatever radius this is, it's r. So we can parameterize our gamma, because notice on gamma, all the z's can be written as r times e to the I theta, where theta is on the interval, and we're going from minus pi over 2n all the way up to 0. So our z's, all our z's on gamma can be represented this way, and let's differentiate both sides to obtain our dz. So that's equal to I times r e to the I theta d theta. Alright, so now let's plug everything into our integral. Let's drop out this limit first of all, and we'll apply the limits later. And I also want to take the absolute value of this integral, because we want to start finding upper bounds for this integral. So now if we plug everything in, we get the absolute value of the integral. Now we're going from minus pi over 2n all the way up to 0. Of e to the minus, now z becomes r e to the I theta, so r to the n e to the I theta n, so raising all of that to the nth power, and our dz becomes I times r e to the I theta d theta. And notice we're dealing with a real variable over here, which means we can use the integral inequality to exchange the integral and the inequality to say that this is less than or equal to the integral of the inequality, so the integral from minus pi over 2n all the way up to 0, of the absolute value of e to the minus r to the n, e to the I theta n, and then absolute value of I is just 1, absolute value of r is r is a really big number, positive big number, so let's stick that out the front. And absolute value of e to the I theta is exactly 1, so we can end it right there, d theta. And now I want to use some Euler's formula up here with the e to the I theta n. And now we can rewrite this as r times the integral from minus pi over 2n all the way up to 0 of the absolute value of e to the minus r to the n. And now the first part of the Euler's formula is the cosine of theta n. And then the second part is I times the sine of theta n. So we have minus I r to the n, the sine of theta n, d theta. Alright, and now what I want to do is I want to split this exponential up because we have e to the something plus e to the something. So we can use that multiplicative identity to say that it's the same thing as e to the first bit times e to the second part, like so. And since we have the product of two things, we can split up the absolute values a little bit. So now we have the integral from minus pi over 2n all the way up to 0 times r on the outside as well. And then we have the absolute value of e to the minus r to the n cosine of theta n. And then the absolute value of e to the minus I r to the n sine theta n. But notice, r to the n is real, sine of theta n is real, which means this whole part is real, including this negative. And whenever you have e to the I times some real number, the absolute value of that is always 1 because you're on the unit circle, so we can ignore that. So we have a d theta to end it off. And notice one cool thing, this thing is all real, and the exponential function is always positive, so we can drop the absolute values, like so. And now we're left with this integral to kind of mess around with. And this is a little bit hard to anti-differentiate. Of course, we don't have any imaginary numbers flying around everywhere anymore, so this is a real integral that we can evaluate. And I also want to point out that this integral is greater than what we initially had. So this absolute value of the integral over gamma is less than or equal to this integral that we currently have. So let's move that back up. So this is less than or equal to r times the integral from minus pi over 2n all the way up to 0 of e to the minus r to the n and cosine of theta n d theta. Right, cool. And now what we want to do, this is very hard to anti-differentiate, so we want to estimate this integral further. And I want to in particular look at this exponential function. If we have e to the minus something, because the part in the exponent contains the variable, so let's look at e to the minus x, for example. If you graph this function out, it's going to look something like this. So it's always decreasing. And if you pick a point A and you pick another point B, where A is less than or equal to B, then notice that if you take the output, then e to the minus A is always greater than e to the minus B. So as you can see, e to the minus a is up here, and it's greater than or equal to e to the minus b, which is down here. And why is this useful? Well, if we have some function in here, so let's call it f, and if we can find an upper bound for this function g, then the integral of this function f will be less than or equal to the integral of g. So if f is less than or equal to g, then the integral of f is less than or equal to the integral of g. And we want to find this upper bound. And how can we do that? Well, notice we have e to the minus a something, and we want this e to the minus something to be less than or equal to something else. And in particular, if we let this e to the minus something, if we let this current function f be equal to some e to the minus b, then all we have to do is find some kind of e to the minus a that's greater than or equal to e to the minus b. And in particular, for this to happen, our a has to be less than or equal to b. So if we look at the exponent over here, just this part, if you look at this term, if we can find some kinds of expression that's always less than or equal to r to the n cosine of theta n on this interval, then we can find a new upper bound for our function f. So that's the idea. Alright, so what's a function that's always less than or equal to r to the n cosine of theta n on this interval? Well, if you take a look at the graph of, let's just take a look at the graph of cosine of n first, cosine of theta n first of all, because r to the n is just some constant, it's just some kind of scalar. So if you look at the graph of cosine of theta n, you're going to get something that looks like this. And in particular, notice that on the interval minus pi over n to 0, it's precisely this section over here. Because if you just imagine having just cosine of theta, so if this is the theta axis, then you're going to get an intercept at minus pi over 2, because cosine of minus pi over 2 is 0. But then if you scale, if you dilate everything by a factor of 1 over n towards this vertical axis, then you also move this minus pi over 2, you also dilate it in by a factor of n. That's why you have a division by n. And you can also test that if you want to. If you plug minus pi over 2n into this function, the n's will cancel out and you're left with cosine of minus pi over 2, which is 0. So this function, if this function is cosine of theta n, then this point is a minus pi over 2n, and you also get 0 over here. So what's a function that's always less than or equal to cosine of theta n? Well, notice if you construct some kind of line that runs from the x-intercept to the y-intercept, then that line is always less than or equal to cosine of theta n. So let's try to find the equation of that line. Well, for cosine of theta n, you know the y-intercept is 1. So if you call this the y-intercept, then right here y is equal to 1. And you also have the x-intercept, which is pi over 2n, or minus pi over 2n. So if you take a look at the gradients now, well, gradients is rise over run, so 1 divided by this run, so that's going to give you 2n divided by pi. So that's the gradient, so in particular y is equal to that gradient times x plus the constant, but the constant is exactly the y-intercept, so plus 1. So what did we just find? We found that for all this should actually be theta because we're working with the theta axis. So for all theta on the interval minus pi over 2n to 0, cosine of theta n is always greater than or equal to 2n, or 2n, over pi times theta plus 1. So this implies that e to the minus r to the n times the cosine of theta n is always less than or equal to e to the minus r to the n times 2n over pi times theta plus 1 by this relationship that we have. So now let's insert this into our integral, and we get that this integral is less than or equal to r times the integral from minus pi over 2n to 0 over e to the minus. And now instead of this original function that we have, we're going to replace it with this one over here, so e to the minus r to the n, and then the 2n over pi times theta plus 1, like so, d theta. Alright, very fine. And now notice that this is extremely easy to integrate. Of course, we do have a bunch of random constants flying around everywhere, but this is easy to anti-diff because we just have e to some kind of linear function in terms of theta. So if we anti-differentiate this, then we are going to get r, and then we have, if you use some chain rule, then we have integral of e to the something is just e to the something itself, so e to the r to the n 2n over pi times theta plus 1. But then in order to compensate for the chain rule, you have to divide by the derivative of the inside. So let's see, what's the derivative of the inside? We're just going to have the constants that are multiplied outside of this theta, which should just be minus r to the n, and then 2n over pi, like so. I believe that should give you the correct antiderivative. If not, I'll probably put an annotation somewhere. Hope that's right. But we have to evaluate this from minus pi over 2n all the way up to 0. And since this is a constant, then we can just leave it outside. We can put it outside because it's just a constant. This should have been 2n, not 2 pi. So 2n over pi. Alright, and now let's plug 0 into here. If we plug 0 in, what are we going to get? Well, this is going to become 0, and we're left with e to the minus r to the n. So this is now equal to, let's clean things up out here a little bit as well. Let's flip the pi up to the top, and we're going to get pi over 2n, and then r to the n minus 1. And then we'll also have a negative out here. So if we plug 0 into here, we're just going to get e to the minus r to the n. And if you plug minus pi over 2n into here, then notice that 2n, right in here, I don't know why I keep writing 2 pi, 2n over pi times minus pi over 2n. Notice that's exactly minus 1 because these cancel out, leaving us with just this negative. So we have minus 1 plus 1, which is 0. And then e to the 0 is just 1. So we have e to the minus r to the n minus 1, like so. And that should be the integration done for this integral. So notice this integral is less than this integral, which evaluates to this thing over here. And now let's see what happens. So we know this integral is less than or equal to minus pi over 2 pi r to the n minus 1. And then let's actually get rid of this negative by interchanging the stuff on the inside. So 1 minus e to the minus r to the n. Okay, and remember we wanted to apply the limit on this integral. So if we take the limit on both sides, so limits as r approaches infinity on the absolute value of the integral over gamma of e to the minus z to the n dz, that's less than or equal to the limits as r approaches infinity. Pi, let's see, what did I do wrong over here? I believe this should have been an n, not 2 pi, so 2n, like so. So we have pi over 2n r to the n minus 1, and then 1 minus e to the minus r to the n. And what happens as r approaches infinity? Well, notice if n is greater than or equal to 1, yes, notice if n is greater than or equal to 1, then we have r to some positive number. But as r approaches infinity, if you raise a positive number to a positive number and take the limit, then this thing is just going to blow up to infinity. So we have something over infinity, which is 0, and what have happened in here? Well, that's just going to turn into 1 minus 0, which is just 1. So in fact, this just goes up to 0. So we have the limit as r approaches infinity on this integral is equal to 0. But notice this is, we have an absolute value, which means this thing is always positive, and the only way for a positive thing to be less than or equal to 0 is if it's 0 itself. So this implies that the limit as r approaches infinity on the absolute value of the integral over gamma, I'll just write it like that, is equal to 0, and the only way for this thing to be equal to 0 in the absolute value is if the integral itself in the limit is equal to 0. So this implies that the limit as r approaches infinity on the integral over gamma is equal to 0. So hence we've shown that the integral over gamma is equal to 0, and remember that one equation we had that the integral over psi plus the integral over gamma is equal to the integral from 0 to infinity, and on the left hand side we had the limit as r approaches infinity. Well, in the limit as r approaches infinity, we know this integral vanishes off to 0, which means that this integral over psi in the limit, so limit as r approaches infinity on the integral over psi, which is exactly the integral that we had that went from 0 to r e to the minus I pi over 2n of e to the minus z to the n dz, that's equal to the integral from 0 to infinity of e to the minus z to the n dz, which is our goal integral. And so let's just replace the variable. Let's just keep it as z, why not? So we'll just keep that variable as z. So we've just shown that. So we've basically gotten to our goal integral over here. So now we can write this as being equal to e to the I pi over 2n, and then the integral from 0 to infinity of e to the minus z to the n dz. Right, and remember, as I said before at the very start of this video, the integral in this form is really nice because now if we perform a substitution, if we let t be equal to z to the n, that means dt is equal to nz to the n minus 1 dz, but that's equal to n times z to the n times 1 over z, so I guess z to the minus 1 dz. But notice z to the n is exactly t, so we have nt, and then z to the minus 1, well, we know z is equal to t to the 1 over n, which means z to the minus 1 is t to the minus 1 over n. And then this is dz. So if we isolate our dz, we have dz is equal to 1 over n, and then this t becomes t to the minus 1, this t to the minus 1 over n becomes t to the positive 1 over n. So we have t to the positive 1 over n minus 1 times dt. So if we plug all of that in, we get now the integral from, actually, we still have this extra factor up the front, so e to the I pi over 2n times the integral from 0 to infinity. Notice n is greater than 1, so it's positive, so if we plug 0 in, it's 0, if we plug infinity in, it's infinity. We have e to the minus z to the n, we said that was t, and dz becomes 1 over n t to the 1 over n minus 1 dt. And let's rewrite this integral a little bit. This is e to the I pi over 2n divided by n, integral from 0 to infinity, t to the 1 over n minus 1 times e to the minus t dt. And notice this is exactly gamma of 1 over n, because we have integral from 0 to infinity, t to the something minus 1, and then e to the minus t dt. And this, in fact, is just gamma of that something. So gamma of 1 over n. Right, very, very nice. So now we've shown that all this stuff, so our integral from the very start, is equal to e to the I pi over 2n over n, and then, well, this integral just becomes a gamma of 1 over n, like so. Alright, very nice. So we've basically evaluated this generalized integral, I guess, and now in order to obtain these two integrals, we just simply take the real and imaginary parts respectively, or real and imaginary parts. So now if if we look at the integral from 0 to infinity of sine of x to the n dx, that's exactly the imaginary part of the integral from 0 to infinity of e to the I x to the n dx, which is equal to the imaginary part of e to the I pi over 2n over n times the gamma of 1 over n. But notice the only kind of complex part in this expression is this e to the I pi over 2n. So if we take the imaginary part of that, then this just becomes sine of pi over 2n. So in particular, we get 1 over n sine of pi over 2n times gamma of 1 over n. So gamma of 1 over n, And we can do the same thing for the integral of the cosine of x to the n. So integral of cosine of x to the n dx is equal to the real part of the integral from 0 to infinity of e to the I x to the n dx, but that's the real part of e to the I pi over 2n over n times the gamma of 1 over n, but that's equal to 1 over n, then the only imaginary part, or the only complex part is this exponential function. So taking the real part of that, that just becomes the cosine of pi over 2n, and of course we still have the gamma of 1 over n. So that's basically the final result for this video. We've evaluated the two, I'll just call it the generalized Fresnel integrals. So this is really quite nice. It gives us a nice generalization, and we're actually going to be using this result in a future video to kind of evaluate another cool generalized integral. So yeah, that's pretty much it for this video. Hope you guys have a wonderful day, and I'll see everyone later. Bye bye.